Okay. Okay. Here, she beat. Wow. There was like an instantaneous. Hello. Hello. Well teleported there. Hello, Lila. Oh, and are you? Wait, is that John Jay? No. Is that? Yeah. Are there? Oh, okay. Are you? Okay. So and there's Mike. I'm going to say that's the Golden Gate Bridge. Hello. Hello, Michael. Excuse me. I'm saying that's the Golden Gate Bridge until. All right. All right. Until further. And there's Sophia. She always. Sophia flies under radar. Yes. I mean, there's and Mancha. This class has a high percentage. I'm not okay. Anyway, yes. So hello, Lila. Hello. Oh, interesting. So wow. So Raymond is also in San Francisco. Excellent. And right. Okay. Excellent. And but Lila, are people with you? I'm just curious. Are people with you at no. Okay, okay. Excellent. Remind me someday to, oh, and Tania, thank you for saying hello. I see you in the chat. Thank you. Oh, who else did I? So Sophia Mantra, hello, Joyce. Yeah, you guys have such a high. I'm so pleased with the whole video thing in this class. Seriously, it makes such a difference. I feel like I know you people almost. So hello, Joyce. Hello, Mantra. Hello, Sophia. Hello, Michael. Hello, Lila. Hello, Raymond. Hello, Shen and Montserrat with the awesome avatar. Oh, Montserrat. I see what's going on there. I think. Wait, is that a Pokemon? Wait, no. It's hard to. Okay, anyway. Hello, and Tania got the avatar and the chat. Awesome. Thank you. I know this always plays out so weird on the videos, I know, but it's oh, and Luis that and wait, Jerry with the avatar. Ooh, cat. Um, I'll and Jadith with what also counts as an avatar, and someone's on their phone, which is fascinating. I don't know how that works, but okay. So Luis, good afternoon. Shen, good afternoon. Montserrat, hi. Jadith, hello. Samaya, yes, Samaya, hello. And Raymond's coming in. Sorry, hello. I mean, hello. Good afternoon, Tania, with the triple, or do I guess I already acknowledged that? Yes, with the chat and the avatar or the picture. Good afternoon, Camille, with the everything. Leah, good afternoon. Wait, I always do that wrong, but it is Leah, not Leah, right? It is Leah, not Leah. It's Leah, not Leah. Right, yes. Good afternoon. And Jerry, good afternoon. Okay. I think that covers. And obviously also hello, Danielle. And hello, I think that's everybody. Okay. Oh, yeah. Oh, no, no well, you're not really late, Raymond. Well, okay. Yes, haha. Um, really weird. No, I'm not gonna go there. All right. Oh, more people coming, Nico. Okay. All right. One thing to get out of the way, I'm gonna put in the chat right now, just to be clear. Oh, well, um, sheepish note from me in the chat, which hello, Nico. Good to see you. Good to see you. Thank you for the acknowledgement. All right, right. And I'm a little, oh, thank you, Raymond. Okay, thank you. And yes, um, am I blaming that a little bit on my medical situation? Yes, a little bit. Can I blame it fully on that? No, but I'm asking your patience in the name of my medical situation, which is starting to challenge things. But anyway, they're not forgotten. You get the point. They're not forgotten. I promise you that. Again, it's that time of year where I'm very impressed that you're all here. Like it gets much harder for you guys at this time of year. It gets harder for us as well. We're both going to be sympathetic to each other about this time of year. Again, part of what that means, again, just to remind you, is you don't have anything new really to do for me for a little while. You're trying to tie up loose ends or catch up intellectually or academically with any old revisions or work you owe me. I'm trying to catch up with you, et cetera, et cetera. That goes on for a while. Oh, thank you. No, I appreciate it. All right. No, thank you, Raymond. I don't mean to, but thank you, Raymond. I appreciate it. Okay, but just want to be clear. And I don't mean to take up class time with it every time. I just want you guys to know, like, I know it's a thing. Okay. Um, okay. So let's get back to like physics. Was there any other thing? Any other announcement? Oh, okay. No, I don't think there's any other. I mean, you let me know if there's something logistical. Oh, I guess well, we'll get back to physics, which is this. All right. We're going to get to physics now. Where we are in physics conceptually is we're talking about electrostatic fields, specifically electrostatic fields from point charges. And we're about to today start dealing with the math of that, and the reason I wrote sine squared theta plus cosine squared theta equals 1 is that, oh, wait, no, I'm glad wait, pause for a second. I see Michael's question in the chat, and I'm very glad he's clarifying. Wait, so I'm looking at the chat. Wait, homework seven. Wait, I'm glad he's asking, because no, I think I've been unclear about the homework lately. Hold on. Is homework 7, if homework 7 is the E-Fields homework? No, what's homework 7? Oh my God. No, all right, wait, thank you, Michael. I'm going to change that right now. I think I know what you're saying. Hold on, everybody. Oh, if homework, I'm so glad thank you for catching that. Hang on, let me look. No, you're right. Good job, Michael. I'm going to change that right now. So what he's saying is, all right, so look, so the answer is no. I'm going to change it right now. Next Wednesday's Thanksgiving. All right. Can we afford this? I'm going to take a risk right now. Monday. Well, all right, all right. No, all right, all right. No, I'm really glad he's asking. Okay, okay. Hold on. So this Monday is it? Okay, a little risky what I'm doing here, but in fact, wait, I'm going to do one other web. Sorry. Okay, to be clear, or to try to be clear, the homework that's on the docket right now is homework 7. Excuse me, is homework 6. The one that's on the docket right now is homework 6, like the one that's called from G fields to E fields, or it's called E fields. Okay, that's what we're in the middle of talking about right now. That's what was like technically due last week or something, and that wasn't outrageous because like that's what we're talking about right now. Again, of course, to any of you and any of you, excuse me, who made any attempt on homework 6 at all when it was due can still get all the points on homework 6. In fact, let me be even further clear about that. I'm falling a little bit behind, so I haven't given any feedback on it at all. But if you turned in homework 6 on time at all, you've already gotten 51 out of the 65 points. And 51 is a signal to you and me, which says you did it on time, like you did a rough draft on time. Now, and you know in your heart whether you think you did all of it or did it all correctly or not. You're watching me as I go over it in class, like right now today. You're seeing in class whether there's more that you can still do on it or correct on it. And so if you know that there's more that you can correct or do, you're based on what we do in class, like including today, then you're just going to take it upon yourself to re-upload to get the rest of the 65 points, right? Okay, this is all of you who have turned in homework 6, any draft of it at all on time. You've gotten 51 points already and you've gotten no feedback. It's on you right now to see if there's anything that you can do based on class where you can re-upload and get the rest of the points, or if not, if you think you already after class today and Wednesday, it looks like you did it all perfectly, you think, and you haven't gotten any feedback from me and you only have 51 points on it, then you're just going to take what you already did and you're just going to like re-upload it or gently remind me in the thing to say like, I think this is perfect. What do you want me to do next, prof? And I'll look at it and be like, oh, well, no, I think you're still confused on this. And I'll tell you, or if and when I don't, or if I'm like, oh no, yeah, they're right, then you just get all the rest of the points. Now that's on homework 6. Now, if you didn't turn in anything on homework 6 yet, you still totally can. And you'll still get a huge amount of points. You just won't get all of them. Okay, that's homework 6. That's what we're up to right now. And that's and that's what we're literally about to continue going over right now. What Michael's asking about is homework 7, which is the next one, which is Gauss's law. He's right. Thank goodness he just caught the fact that technically it was due this Wednesday, but I missed that and I don't mean for that. So I've just extended it to next Monday. I mean, again, I didn't. I extended it till after Thanksgiving because I'm trying to sort of keep my promise that like right now we're all catching up with each other. Okay, and that's like the next topic, that homework 7. It's hard. So that one, we'll get a jump start in class. We'll start talking about it before you have to do it. Thank you, Michael. You can all privately thank Michael for that. Okay, so that will be due after Thanksgiving when we had a little time to start it together. And I just made it worth more points because once you do it, because it's just an opportunity to get more points. And you'll have more time to do it. So okay, so hopefully that's all good news, and thank you, Michael, for catching that. So again, for a while through Thanksgiving, you're just trying to catch up with me, and I'm trying to catch up with you. Yeah, you're right. Oh, okay. So I'm looking in the chat. So yes, what Michael is asking about homework 7 is Gauss's law. It was due this Wednesday, but I just changed it and made it due the Monday after Thanksgiving. Okay, so again, like somebody, and if you, by the way, if you publicly thank Michael right now, that's multiplayer co-op, so you get points for that, whatever. But or if someone could just clarify, that isn't Michael. Could someone just acknowledge that they get what just happened, like that you get where you are now with the homework, like or confirm that it is changed? Yeah, okay. Oh, did I make it November? Oh my God. All right. Thank you, Lila. All right. That's exactly what I need. All right. So I made it November 3rd, not November. Jesus, you're right. I didn't say Jesus. Sorry. Okay. Thank you, Lila. And Lila just got multiplayer co-op. Okay. I meant to say December. Thank you. I'm fixing it now. December. It should be due December 1st. It should be due this. It should be due. Right? Because 18. Yes, I mean to make it December 1st. Thank you, Lila. So you can all now privately thank or publicly thank Michael and Lila. Wait, or check, confirm it should now. Wait, and I changed the point. Whoa, something is. Whoa, I see what's happening. Wait a minute. Sorry. Hold. Oh my God. All right, maybe can we blame this on the chemo? Because I'm losing my executive functioning. Like maybe that's just age. So hold on. I meant to make that higher points. I think I made the other one higher points accidentally. No. Oh, so it just didn't. So please confirm now, whether you're Lila or anybody else, it should be the case that homework 7, Gauss's law, should now be due Monday, December 1st, and it should be worth like 80 points now, not 65. I'm going back to the Zoom screen. Thank you, Maya. Okay. Yeah, okay. Great. So Tanya did.
I see 65 points due December 1st, which is a
Right.
Sunday.
Oh my God. All right. Thank you, Raymond. I'm not saying, oh my God, to you, Raymond. I'm saying, what is going on? All right. Wait. This is such a, what is going on? You're right. It does it.
Also, it says 2025.
Yeah. Oh my God. Oh, maybe that's why oh my God. Thank you.
That's
That's
probably
probably,
why it's Monday for
yeah.
you. Yeah.
Yeah. You're totally right. Okay. So I'm going to try this one more time, but why are the points not changing? All right. So 12, we're going to try this one more time. This is why we have class together. Oh my God. Okay. 80 points. Monday, December. We're going to try this one more time. Okay. Tell me. I'm looking in the Zoom again. I'm looking. Yeah. And all of you, Mantra, Mike thanked himself. All right, fine. That got fine. But all of you, Mantra, oh, Lila, thank you. Okay. Raymond, all of you are participating in this. Like, you all get multiplayer co-op. And I know it's all silly. I know you're all getting sick of hearing this, but like you deserve it. Like, engage, right? Like, you get it. Like, yes. So it still says 60. Oh, no, it's all updated correctly. All right. So yes, please. And any portal that applies, like closing a conversation, but just you can always double dip, triple dip, whatever, just whatever. It's all Tom Nook, Animal Crossing, if that helps anybody. It's all Nook Miles. It's the same concept. Anyway, whatever. Uh okay. Um, um, okay. So thank you. All right. So we're good on that. Thank you, Michael. Honestly, all right. Okay. Now, back to our regular scheduling program. What we're continuing to go over. Well, all right. So we're going to go back to homework 6 now. We're going to start doing some somewhat computationally heavy math with the concept of fields. So there's going to be computation involved. I just, before I switch screens, like on the screen is two things. One, well, I really actually, let's make this really clear. Okay. I just want to summarize what's on the board right now and then I'll switch the screens back to the homework that we're talking about. Uh, but so let me go out of order. Look down at the bottom, what I just added to the screen right now. The equation at the bottom. The equation at the bottom, it says in general, electrostatic field vector is defined to be the net electrostatic force vector divided by lowercase q, right? That is a general definition. It's like super simple, but it's not super easy. And it comes from what we were talking about last week. So let me just summarize again. What I'm saying is, in general, the field is the net force per, excuse me, per object, Like in general, the gravitational field is the net gravitational force per mass. And the electrostatic field is the net electrostatic force per charge, right? Like that's simple, but that's not easy. So for starters, let me remind you that when I say per mass in the case of gravity or per charge in the case of electricity, I mean per the test object, per the second object, or the receiving mass or the receiving charge is what I mean. In other words, conceptual, well, unit wise, if force is measured in newtons, or any kind of force is measured in newtons, then the electrostatic field is measured in newtons per coulomb, right? And similarly, like the gravitational field is newtons per kilogram. That's in units. What that means conceptually is, okay, to stay in electricity now, like our point is electricity. So, like, one charge exerts an electrostatic force on another charge. And by Newton's third law, like vice versa, the other charge exerts an electrostatic force on the first charge. But when you're looking at it, if you're like, hey, this charge, this big charge that I'm calling the source charge, is exerting a force on this other small receiving charge that I'm going to call the test charge, right? That's just designations in your mind. If you're thinking of like what a electrostatic force is something that one charge does to another charge, and the magnitude and the direction of that force is determined by how big the first charge is, like the magnitude of the first charge, the magnitude of the second charge, and the square of the displacement between the two of them, right? Then what field is just what the first charge is doing to any given location, to every given location in space, right? Field is the force waiting to happen. Field is all the information that the force would need in order to become a force. Field vector is the vector that contains all of the information of the force vector except for the information of how big the receiver of this force is, right? Like every time I try to explain it a different way, it gets like more and more like maybe hard, like maybe it gets harder to understand in a way. But I'm saying that if I would have pushed you a certain amount because I'm so big and you're so big and you're over at this location relative to me, then we're saying the new way of looking at it is no, 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 no. Even before you came along to that location, even before you got there, I was already pushing on that location with a certain amount and a certain direction based on how big I am and based on how far away that location is from me. I'm just like already I'm placing if I'm a proton, I am placing a vector at every single location in space, a vector that has a certain magnitude and direction based on how big I am and what that location is in space. And the vector is just sitting there waiting for any kind of test charge, any second object to come along and experience that vector. The vector is literally how hard and in what direction I would push or pull on every 1 coulomb of positive charge. So the vector is sitting there with a certain direction and a certain length. And if what comes along if what comes along to that location, if what comes along happens to be literally 1 positive coulomb of charge, then it's literally going to it's going to be like 1 times the magnitude and direction of that vector. So 1 coulomb of charge will just experience a force. It's like 1 Newton per coulomb times 1 coulomb will make 1 Newton of force. Every 1 coulomb of test charge that arrives, that might or might not arrive at that location, will experience that amount of force in that direction. And so if a 2 coulomb test charge comes along to that location, then it'll be 2 times whatever that force vector is. So the field is the force waiting to happen. Field is something I do to you. Sorry. Force is something I do to you. Field is something I do to a location. Field is force per charge. Like that's what we decided last class. We first sort of invented this idea for mathematical convenience, but then we decided at the end of last class that actually it's not just a mathematical convenience. It's actually something we have to believe in at some level, because somehow it does seem that the information of every 1 single object that exists in the universe somehow exists at every other location in the universe. And we know this because every time another object appears anywhere else in the universe, it gets pulled or pushed on by the first object by an amount and in a direction that totally depends on this precise details of that information. So the information's already sitting in space somehow. The information sitting in space we call a field. We imagine the field. So last thing I'm saying, just so you can picture it, I'm saying the minute you put a proton in space, anywhere in the universe, in the lab, in outer space, whatever, the minute there's a proton in the universe, then there's automatically a whole bunch of arrows that are automatically at every single point in space. There's an arrow sitting at that point in space with a certain length and a certain direction, indicating the force waiting to happen due to this original proton that's sitting there. Like, now, am I literally saying that there's like literally arrows in space? No, but I'm saying that there's information in space due to that proton. And I'm saying the most convenient, productive way we have come up with yet as human beings to picture that information is with arrows. Well, actually, that's not even true. We eventually connect the arrows together and make these things called lines, called field lines, which we'll get to next. The point is, they're representations in our mind. The field is a representation in our mind for the fact that somehow the information of one object exists in space even before a second object comes along to experience it. And then once a second object does come along, it experiences that field information as a force. Okay, so I'm looking at the chat. So field is force per charge. Now, last thing, now where this has to do with equations and stuff, like field is net electrostatic force per charge, or gravitational field is net gravitational force per charge. So now in the case of point charges, now I'm going to slow down. Remember, in the case of point charges, we have an equation called Coulomb's law. The force between 2 point charges. It's not written on the board right here. I don't want to squeeze this board anymore illegibly. But remember from like last week, and like the Coulomb's law for the electrostatic interaction between 2 point charges is that F sub E equals 1/4 pi epsilon naught times capital Q1 times lowercase q2 all over r squared, like times the r hat unit vector, right? That's the electrostatic for what I'm trying to emphasize is that equation from last week that we're about to use again in this homework sheet. That equation, the Coulomb's law, that is the electrostatic interaction between 2 point charges. That's all, that's huge, but that's all it is. It doesn't tell you the interaction between two like wires of charge or two plates of charge or two spheres of charge or anything like that. It's like the law between 2 points of charge. Therefore, if we are talking about points of charge, as we will do in the rest of this homework assignment, but we won't do in the next homework assignment. In the rest of this homework assignment, we're concerned with point charges. Therefore, the equation for field, if you're talking about point charges, is what's on the board right here. Like 1/4 pi epsilon naught times Q over r squared times r hat. Like, okay, I'm just trying to emphasize that is what, like what's always true is field is force per charge. What's true in the case of point charges is that that becomes constant times capital Q over R. In other words, the inverse R squared law only applies to points. Please know. I still remember when I got this wrong on an exam of my own when I was an undergraduate student. Like it's an important thing to be aware of. Okay, and then last thing I know someone's here. So the red. Whoa, I don't even know. Okay, let's watch whoever enters now. Hope. Oh. So then why did I write sine squared theta? So I'm moving on now. Why did I write sine squared theta equals cosine squared theta equals 1? Like, what's that got to do with anything? That's just a cute way. That's a reminder. What is that? It's true, right? It's a trigonometric identity. What does it have to do with anything? Well, it's the one trigonometric identity that actually, when you really break it down, what that is SOHCAHTOA and Pythagorean theorem combined into one statement. I don't want to get off. I mean, it's actually a really beautiful statement. I don't want to get off all on a rabbit hole, but that's my cute. Whenever I write that, that's my cute way of saying, by the way, vector stuff still applies. Like anytime we have something that's a vector, as we do now, the field is a vector. The field from a point charge is a bunch of vectors everywhere in space. So vectors still add like vectors, no matter what. They add the same way that displacement vectors add, that velocity vectors add, that force or acceleration vectors add. So when you're adding vectors, it's still really important to know that the sum of two vectors ultimately is the Pythagorean sum of the sum of their horizontal components and the sum of their vertical components, all of which I'm about to do right now. And so SOHCAHTOA and Pythagorean theorem still deeply apply to field vectors. So that's just like my way of whenever I say sine squared theta plus cosine squared theta equals 1, that's just basically a way of saying, remember, vectors are still vectors and obey everything that they need to in right triangles. And that's what's about to happen as we turn to the homework now. I'm going to just remind you where we are and just do the screen share. And also oh wait, the person who just joined us, was that like a bomber? Wait, is that person gone now? I'm a little concerned. Okay. They're just trying to get like cheap, free physics education. I know, I used to do that too. Not. So screen share, bear with me for a second. I'm just showing you exactly where I want to be right now. I want to be right. Okay. So where we're going to now is this. Right? This is the middle of, sorry. What we're going to now is this, the middle of homework 6. Like what we did last week was this, yes. And all that was meant to just establish like what the concept of a field is, which is a force per charge. But so now we're going to like deal with field on a computational level. Okay. So what we have here, and we're going to solve it. And again, this is like your homework. Like so many of you already made an attempt. You'll find out now if your attempt was right. If you nailed it, great. Just remind me I nailed it. There's nothing more for me to do, and I'll give you all the rest of it. And if not, you'll find out now. So what we have here, excuse me. So what we have here is we have an XY plane. We have 2 point charges of differing magnitudes stationary in an enormously spacious XY plane, okay? Or like it says. So we've got these 2 point charges. Let me start by saying both of these charges are source charges. Both of these, and this is super confusing to people until it isn't. The given in this problem is that we have a point source, like somewhere, that's creating field everywhere in the universe. Then we have this other point source that's creating field everywhere in the universe. And then we are going to some location in this XY plane, and we're asking ourselves, what is the net electrostatic effect of both of these charges on us at this arbitrary location? Okay, I'm going to try to draw that in a second, but so we are not asking what is one charge doing to the other charge. That is not what's happening here, even though that may seem that way to many of you. And if you think that, I'm not criticizing you, I'm just trying to clarify. We're saying that every point in the universe is the source of field, every point. So anywhere, once you're in the universe, you experience, and this is why, let me back up, why I keep defining, why I keep saying field is the net electrostatic force per charge. Field necessarily is the summation of all and any contributions that come from any sources at all. Field is what you experience if you are a test charge somewhere in the universe due to any and all sources that are like anywhere around doing anything. So what we're going to figure out right now is what is the field at the point zero, at the origin of this coordinate system. What is the field at the point 0, 0 due to the vector sum of the 2 point sources that have been given, the Q1 and Q2. I hope, and stop me if that's not clear, but it's not about what one source is doing to the other. It's about what the combined effect of both sources so let me put it one last way and then I'll move on. We're really asking if there were a positive 1 Coulomb test charge at the origin, in what direction and with what strength would it be pushed or pulled due to the combined effect of this Q1 and this Q2? That's what we're asking here. So we're going to have to add 2 field vector contributions together to get one final field vector. In the end of the day, what we're doing is just adding 2 vectors together. I mean, that's all, like you did at the beginning of Physics 203. We're just adding 2. We're adding 2 vectors together to get a third vector. Like that's all we're doing. We're now, it's like heavy computationally because field vectors have a lot more math involved in them than like a displacement vector or a velocity vector, but that's all we're doing here. So okay, I'm going to switch screen. And last thing, so I just made a table or tried to make a table to organize the information for you, but I realized the table just so you can read the table. People always get this. I apologize. It's just trying to say, it's just a table. So it's trying to say that source Q1 is a charge of magnitude positive 5, and it's at the position 5, 4, position positive 5, positive 4, and the other one is at position 10, 3. I know that looks like a 4/3. That's just a bad like copy paste thing. I apologize. It's not 4/3. It's just 5, 4 and 10, 3. And if you did your whole homework thinking that was 4/3 somehow, and if that's your only error, like just tell me, and like I'm not gonna punish you, just tell me and fine. But you should also note the reason that this thing has been copied and pasted and fixed it is that this thing I'm about to go over tends to be a problem on the final exam. Like this whole, just because it's just fundamental enough and computationally heavy enough that being able to add up so we're only going to do this once, but I'm going to like take all period to do it. So this is just a good problem to know how to solve for the final exam. And that's like why I've changed the numbers a million times in history. Okay, just so what are we doing? We're adding 2 field vector contributions to get one final field vector. And this is all from point charges. This is okay. So if you look up Khan Academy videos or anything for like help with this, what we're talking about here is the field due to a pair of point charges or point sources. That's what we're doing here. Okay. All right. So I'm going to switch. Okay. So I'm going to switch. I'm going to say one last thing, especially if you ever want to look up how to get help with this. I'm calling the origin like the location of interest. You need to understand like that the location of interest could be any location. It's an arbitrary location where, any other location we pick, we could still get an answer. We just get a different answer. I'm picking the origin as a straightforward, but whatever that location is where we're measuring the field, I call the location of interest. Most websites and textbook resource and stuff will call that point the field point. Okay, field point means location of interest. Just they're synonymous. Um, okay, so I'm going to switch. Okay. I mean, I'm going to start solving now, obviously. Okay. First of all, I'm going to draw a couple of. Oh, wait, is it still? I'm looking in the chat. Oh, okay. And I'm going to switch the screen. Sorry. I'm going to draw a couple of pictures here. These are pictures of the situation, partly to help you with the final exam, but also just so that you can have perspective on what the heck is going on here. So, well, and also because it asks, but so um, okay, right. So this is a basic situation. Now, it's all in the first quadrant. That's sort of, I don't know if that's good or bad, but it's all in the first quadrant in this case. Obviously, there's no rule that it has to be. Um, I'm going to draw a couple first. So first, I just want to make it clear to you, like, what's really happening is something like this. And this is going to get sort of crowded. So as I say, after I'm done making this point, I'm going to erase it and draw a different thing. But I want to make it as clear as I can to you first that, and stop me if you don't understand what I just did. I'm just trying to represent the situation. I'm saying that the first look at Q1. Q1 is a positive test chart. I have a positive source. I'm saying that automatically it makes its own field or its contribution to the universal field. And what it does is at every single point in the universe, it places a little field vector. And the field vectors follow a pattern that I'm trying to show you. Just look at Q1, the blue lines. Like, notice that all the field vectors from Q1 all radiate out from Q1. They radiate out, meaning that anywhere you are in the universe, if Q1 were the only thing in the universe, wherever you are, there'd be a little vector at your location that would be pointing outward along the direct path from Q1 to you, right? Like right along a radial line and outward. Why? Because wherever you are, you'd be pushed by Q1 along the line connecting Q1 to Q2, like that R hat business. Why would you be pushed out? Because the whole idea of the field is always a prediction of what would happen to a positive 1 coulomb of test charge. I'm trying to emphasize right now, before I go any further, that the field, by convention, by hypothesis, assumes, or it makes a prediction. It's the information of what would happen if a positive 1 coulomb of charge were at a certain location. So since Q1 is a positive source, right? I'm not saying Q1 had to be, but it is a positive source. A positive source would always push on a positive test, right? Like going back to last week, or going back to what you know from chemistry, positives. Like a positive times a positive is a positive. It pushes out along the direction of R hat, right? So positive sources always push out. What does that mean that a negative source does that mean that a negative test couldn't come along and experience this field? No, it doesn't mean that at all. A negative could land in one of those spots. But what a negative would do ultimately would be accelerated in the opposite direction of the field line. In other words, the field is positive, and then if you put it back in the equation, if you put it back in the equation, you get a negative times a positive. So it would be taken care of. I'm just saying this is a prediction of what would happen to a positive test. Okay, that's similar. And notice the arrows, the field vectors. So those blue arrows that I'm drawing from Q1, they're just like a swath, like a cross section, a representation. Like any point you pick, there's an arrow everywhere, but that's just enough arrows to give you an idea of the pattern. The pattern is that all of the field vectors point out from Q1, and notice they get smaller and smaller as you get farther and farther away, and they get smaller in like a uniform way, like right, depending on every time. Like all the arrows that are to a certain distance are the same length as you get, and this is all the inverse R squared idea. The farther away you are, the smaller the force would be. So each one of those blue arrows is what would happen to a positive 1 coulomb if it were to find itself at that location. And again, what we're believing now is that arrow is there whether or not the test arrives at that location. If a test arrives at that location, then it's a force. Until that time, it's a field. I hope that makes some sense. Now, if you go over to the Q2, Q2 is creating the same kind of situation. Well, same kind of situation. Only all there, the arrows are pointing in. Why? Because Q2 is a negative source. And we're still always obeying this convention that whatever the field is a prediction of what would happen to a positive test. Always, no matter what. The field is what would happen to positive 1 coulomb. So if your source is negative, then you would pull in a positive test. Yes? So the field vectors always push out from positive sources, and they always pull in from negatives. Same thing with the negatives. All those arrows should get smaller and smaller as we get farther out. It's just getting so crowded, I'm not drawing that many arrows, but they too would get smaller. And frankly, last thing that I did not really capture well in this diagram, but if you're still like paying attention, God love you, Quark love you. Then actually the truth is the arrows surrounding my Q2 should really be like 40% smaller than the arrows surrounding my Q1 because the Q2 is 40% magnitude of charge, right? I mean, the Q1 is a +5. So it's plus, that means the arrows go out, and it's 5. So that means the arrows should be big. But the Q2 is -2. So the arrows really should be smaller. But the diagram is like already crowded enough as it is. I'm not gonna, but that's a sketch of what's going on in general from these two. Stop me if you don't follow. But now I'm gonna that's just like a general sketch. Now, and it's generally sketchy. Now I'm going to erase that. No, I'll leave that and make a new. I'm just thinking about the PDF, your PDF. Hold on 1 second. No, yeah, it's on you. All right. So if it were perfect, I'd leave it for the PDF, but it's not perfect enough to justify it anyway. So now I'm going to do a different diagram. What you're what you're concerned about, see, that's all interesting and hopefully helps you get perspective. Oh, well, let me. Okay. But that's a lot of information that's helpful for larger perspective, but a lot of that information doesn't help you actually solve the problem. The problem is asking what, hello. The problem is asking what's going on right here at the field point, right? So there's a point source at 5, 4. There's a point source at 10, 3. Now at the origin, there ain't nothing there. At the origin, there is no charge, but we're asking we're asking what's the field at the origin. So we're in effect asking what would be the force if there were +1 coulomb of charge at the origin. So I'm only concerned about what's happening at the origin. So to zoom in on this, what I know is that Q1 is creating an arrow right there. Yeah, yeah. Q1 is placing a right, like if you just like all the other arrows from Q1 are interesting and real, they're in the universe, but they're not affecting like the question here. There's an arrow pointing like down and to the left at the origin. Why do I know that? Because like if I connect Q1, if I think of the line, the R hat, the R vector that's connecting Q1 to the origin, there's a line there, and so the field vector has to point along that line and has to point out because Q1's pushing. At the same time, Q2 is pulling on the origin. So there's a vector coming out of the origin this way, but a smaller arrow. Why do I know it's smaller? Number one, Q2 is a smaller magnitude. Also, Q2 is farther away. So this is all I'm just qualitatively explaining what's happening in K in 1/4 pi epsilon naught times Q over R squared. Each one of these is making its own Q over R squared, R hat. And we're going to add those two vectors together to get our final vector, right? So that's the situation. That's your like DFP diagram, really, that helps me visualize what's going on. I've got a push on the origin from one, and I've got a smaller pull on the origin from the other. And what I got to do is we must add these vectors. Add these field, really technically they're called field vector contributions. Right? We've got to add these two together. We have 26 minutes. Okay. So I'm going to draw one more. Well, I'm going to draw a lot of diagrams. I'm going to draw another diagram just for visual. So visually, what we're doing is this. Or graphically, right? Graphically, what's going on is because when you add, right, this is what's visually happening at the origin. But we're going to add those two vectors together. When you add vectors, you place them tip to tail, right? So what's happening, right? Well, I just can't say. I mean, when you add, so if my diagram is drawn at all to scale, which totally is not, you know, the final E vector is presumably pointing, and it really is not drawn very well, but make this a little bit better. In other words, if I drew this perfectly to scale, if you used or you actually had like a protractor and a ruler, then the answer that we're looking for in this whole problem would be the magnitude and the direction of this yellow vector. Like, and if we drew it all with protractor, I'm still not doing it very well. But like if we drew it perfectly with protractors and rulers, then we could just measure the size and the angle of the yellow vector, and that would be the direction in which the field is acting at origin. Now, again, I'm sort of nervous that I keep drawing this diagram so sloppily, but I'm sort of trying to say that if if charge one is pushing somewhat, see, no, I've already making a mistake. Oh no, I'm not. I'm not. I'm making a slight. Well, hold on a second. It's really E2 and E1. E1 is big and going southwest. E2 is small and going northeast, right? So the final, at the end of the day, presumably our answer is going to be southwest. Because the vector that's going southwest is a lot bigger than the other one. So anyway, so with the end of the day, we should get an answer that sort of resembles the yellow vector in this picture. If we don't, it either means we made a computation error or it means that I drew my diagram badly and we have to rethink that. But if you were in a final exam, this is like how you triangulate. You sort of make a sketch prediction and then hope everything is consistent at the end. And if not, you look for where you're doing something wrong. Okay, so now I'm going to analytically add them. Okay. And so we're now going to try to get an exact answer for the electrostatic field vector. It's a vector. So we're ultimately looking for a magnitude and a direction. And the direction means angle, right? And I'm assuming this in this whole diagram, I'm assuming like that this is like east, and this is north, and this is, I think it says this in the problem, and this is west, and that's south, right? So I'm going to get in the end of the day a magnitude, which will be a magnitude will be force per charge. It'll be a magnitude in newtons per coulomb, and I'm going to get a direction, which will be angle and points of the compass, right? That's what I'm looking for. And the way I'm going to do it is by adding together or tallying up the X and Y components of these field vectors and adding them together, just like you would with displacement or velocity. So here's E1, right? What does that mean? E1 is pointing like southwest. That means it's pointing some amount west and some amount south. Yes? At some angle, we'll call theta 1, right? So this is E1x and this is E1y. With me so far? Okay. And they're going to do the same thing to E2, but first let's do it to E1. So what is E1x? Is E1 times, well, E1x is adjacent to the angle. So E1x is the whatever E1 is times the cosine of the angle. This is just like old physics, right? I mean, physics 203, right? So what is that? Well, and similarly, E1y is E1 times sine of the angle, yes? So let's work them out. I mean, we have to. So E1x equals E1. So the magnitude of the whole original electric field. Well, now the problem gives you some hints here to make like the math a little bit easier. Like the constant is 9 times 10 to the ninth. Which frankly, you could make this even easier by approximating that to 1 times 10 to the, I almost want to do that. Well, that's okay. So well, E1x, in other words, equals 1 4 pi epsilon naught Q1. Now I'm just looking at magnitudes now, right? I'm just looking at magnitudes. So the magnitude of that whole constant is approximately that. The magnitude of Q1, the magnitude of Q1 is 5. Oh, sorry, cosine theta. R squared. Okay, what is R squared? Well, R squared would equal R1 squared would equal x1 squared plus y1 squared, right? Pythagorean theorem. Yes, like the display. Stop me if that doesn't, but the distance between the two charges would be the hypotenuse of that triangle. So would be 5 squared plus 4 squared. In other words, 25 plus 16. In other words, 41. That's R squared, and that's all we need, and right? So we'd put 41 down there. Stop me if you. And what would be the cosine of theta? Well, cosine, like I maybe you might think I have to figure out theta first and then get the cosine of it. That could be a thing I could do, but I could cut to the chase. Cosine of theta 1 has to equal adjacent over hypotenuse. So it actually equals 5 over the square root of 41. You see what I'm doing? Right? So this is the x component. I'm gonna have to speed this. Well, the x component. I'll write it again on the next. But right, in other words, I'm doing Pythagorean theorem and SOHCAHTOA to get the x component of the first field contribution. If you're following at all what I'm doing, you'll realize that in order to finish this whole problem, we got to do the x and the y of both and tally them all up together. So I'm going to write this on the next page. What I'm saying is I think E1x approximately equals 9 times 10 to the ninth times, sorry, times 5 um, uh, over 41 times 5 over the square root of 41. That's what I just said a second ago. So that is like 25 times 9 times 10 to the ninth over 41 to the 3 halves. Sorry, I just And I'm rounding, right? So yeah, right. So what is this? This is this is newtons per coulomb. What this is, and I know we have 13 minutes left. This is one out of four components that we need. What this means in English is if Q1 were the only source in the universe, then Q1 is pushing on the origin to the west with this many newtons per coulomb. Like it's if 1 coulomb of positive test charge were sitting at the origin, it would be pushed to the left, to the west, with 856 million newtons of force. That's what this is saying. This is just the horizontal component of the field contribution due to the first charge. So similarly, now I got to speed up, obviously, but that's like, right, I'm going to do the same type of calculation for each component now. So I'll hopefully do it a little bit faster now. So now we go, so stop me if I'm going back, I'm going back and forth between screens. Okay, so you're good so far. So now I do E1Y, right? And it's all the same. It's all the same concept, only now it's just like times the sine of the angle instead of the cosine. So this one is 8.99. Sorry, this one's 9 times 10 to the ninth times the same charge, which is 5, all over the same distance, which is 41, right? But this time times the sine of angle 1. So it's all the same numbers, but this time opposite over hypotenuse. Opposite of, right? So 4 instead of 5, 4 over square root of 41. That's the only difference. Yes? So this one is right. So stop, and you really be ideal if any of you were not only following along, but maybe doing the calculations or checking your homework to make sure you agree with me with, because obviously this is computationally heavy, and Lord knows I've already made 400 mistakes this class, so not including my career choice. So anyway, so you should check my numbers is what I'm saying. Oh my God. And there's a portal. If you catch that one of my numbers is wrong, you definitely get points for that. I think there's a portal called respectfully corrected. But all right. But as far until further notice, I think I'm right. So what we have so far is E1X is 800 million newtons per coulomb. E1Y magnitude, I'm just talking magnitudes here, it's like 684 million newtons per coulomb. It sort of makes sense to me that the y component is a little bit smaller than the x component, because the x coordinate was 5, the y component is 4. That's the only difference between the two. So all right, so that's our x and y components for the first. Now we go to the second. E2x. Well, what is that? Well, I'm cutting to the chase sort of here. That's 9 times 10 to the ninth again. Now it's the other charge now, the other charge. So this is a charge magnitude of 2. I'm just dealing with magnitudes now. We'll explain how to deal with the negative signs soon. I mean, at the next step. But right now I'm just figuring out magnitudes. So the magnitude of the charge is 2. And it's all over now, baby blue. It's all over square root of 100. It's all over 109. 10 squared plus 3 squared is 109 times the cosine of the angle. So what's that? Adjacent over hypotenuse. What's the adjacent for this one is 10. And the hypotenuse is square root of 109. Same pattern as before, just different numbers, right? So now this is on the top, 180. I hope I didn't do this wrong. Yeah, 100. And on the bottom, we have 109 to the So I believe you should check this. I believe we get 1.58 times 10 to the 8th. Yeah, I did it two different ways and I got the same. So I'm looking at the chat to see if any, and we have 7 minutes. Okay. No objections in the chat. I know some of you did this. I mean, a lot of you did it, but I mean, some of you I looked and you did it very thoroughly. So hopefully you're checking it, but I agree with myself so far. Anyway, so that's E1, that's E2x. So now we do E2y. Same thing. But the only difference is it's now the sine rather than the cosine. So it's opposite over adjacent, and the opposite is now 3 rather than 10 over the square root of 109, right? So we get yes, this actually looks familiar too. So I think we get this. Now that's times 10 to the 7 because it's a lot smaller. That y component is a lot smaller than that x component, right? So this is E2y now. Now, we've got 6 minutes left. What do we do with these numbers? Well, this is just like old physics, just like physics 203. We put them in an XY chart. Like the reason we just did that, oh, and I forgot to, sorry, I apologize. I didn't draw a diagram zooming in on the E2y, on the E2, but hopefully you see it's the same concept. We took each vector, we broke it into X and Y components on the theory that every two-dimensional physics problem is really two one-dimensional physics problems occurring simultaneously yet independently, right? So now we can independently add up all these components in an XY chart, right? We're just tallying up the X components and tallying up the Y component. That's what we're, right? They're just adding together. Superposition. So now I'm going to be careful. Now, if you're still with me, Quark, bless you. If you're because I'm tight. If you're still with me, like now I'm going to deal with directions. I've been just dealing with magnitudes up until now, but like where do directions come in? Well, directions come into it from my original diagram and from plus and minus signs. So in other words, EX1, right? We figured out its magnitude was here, 8.56 times 10 to the 8th. But what was it doing? It was pointing to the left, to the west, right? So in my chart, I'm putting that as a negative sign. Negative 8.56 times 10 to the 8th. Because it was a push from the right, right? Then, okay, E1Y was also was down, was south, right? Because it was a push from over there. So it's also a negative sign, whatever value we got, E1Y, cheapers. Okay, right. So it's also a negative sign, negative 6 point, I probably just missed, right? And these are all newtons per coulomb. Yeah. Then the E2s. Now E2, let's look at our picture again. E2 was pulling, right? E2 was pulling up like north and to the east. So both of these components are going to be positive, like, which is weird. Even though it's a pull, they're positive because of the way our coordinate. Think about that on your own. Like, I'm just, well, just think about that, but it's right. So E1Y is positive 6.84. I'm sorry. E2X is positive 1.58 times 10 to the 8th, positive 1.58 times 10 to the 8th. And E2Y, and there's 3 minutes left, E2Y is 4.74 times 10 to the 7th, also positive. So now we just add all that up. We just add it all up. Like, we put in positives and negatives where appropriate, but we're adding no matter what, because we're looking at superposition. We're looking at the sum of two vectors. So we literally add and we get negative 6.98 times 10 to the 8th. And when we add the other ones, well, that's complicated. Right, we get like negative 6.37 times 10 to the 8th, right? Because you have to be careful about the exponents. So with 2 minutes left, what do we do that? Well, that is the X and the Y component of the one total net vector that we're looking for, the field vector. So at the end of the day, what we're saying is the field vector looks something like the thing that we're looking for, the yellow. Right? So the final answer is this. The final answer for E is the Pythagorean sum of those two. And since it's 1 minute left, I'm just going to do it. And you can check my work and tell me Wednesday if I. And the angle at the end is the arc tangent of the opposite over the adjacent. And we're done, I promise. And if you have to go right this moment, then go. It'll be in the PDF, but here's the answer. The angle at the end, the direction is like 42.4 degrees southwest. And that is the that's the answer. That's the answer. If you were sitting at the origin, oh, it's 420. If you were sitting at the origin and you were a 1 coulomb of test charge positive, you'd be pushed with 9.45 times 10 to the 8 newtons to at 42.4 degrees southwest. As we predicted, southwest, I believe our diagram predicted. And if you were a 2 coulomb test charge, it would be pushed with twice that, etc. But that's it. So that's the answer. So thank you for being so patient and flexible as always. I'm hanging out for a minute if there's any questions or anything, but you're free to go and the recording is stopping.